Binary search trees. What is a binary search tree? Well, for one, it's a container object. It's an object meant to store more than one value, and similar to a linked list, it does not use an array. Rather, it stores each individual value in a structure called a node. A node is an object that stores a value as well as references to each of its children. A node can have zero children, it can have one child, or it can have two children, no more. The child on the left is called the left child, and the child on the right is called the right child. Now, notice that the child on the left has a smaller value than the node on top, and the child on the right has a larger value. This is a rule. This is not a coincidence. Any node to the left of 49 must have a value smaller than 49. Any node to the right of 49 must have a value larger, greater than or equal to 49. This is a rule binary search trees must follow. Now, that being said, since 38 and 62 are the children, by definition, that makes 49 the parent node. And since 38 and 62 have the same parent, that makes them siblings. And it doesn't have to stop there. 49 is not the only node allowed to have children. 38 and 62 can also have 0, 1, or 2 children of their own. Same goes for 24, 41, 55, and 73, so on and so forth. All right, now, why would we use a binary search tree? Why can't we just use a linked list or a sorted array list? Why bother with a binary search tree? Well, the reason being is that linked lists and sorted array lists, while they do have their strengths, they also have their weaknesses. And what a binary search tree does is combine the best of both worlds. Now, what are these weaknesses I'm talking about? Well, suppose I have a sorted array and I want to insert the number 7 into this array. Now, clearly the 7 is going to go in between 5 and 9, but I can't just wedge an empty space between 5 and 9. Memory does not work that way. If I want to insert 7 in between those two numbers, then I'm going to have to move each number from index 1 and beyond to the right one by one, before I can fit 7 into the array. Now, if my array only has 6 or 7 values, this is not a big deal. But if I'm Google and I'm using a container that's storing millions upon millions of values, then this operation can become relatively time consuming. Right? Same thing goes if I want to remove a value. Suppose I want to remove the number 13 from the array. Well, I don't want to just erase index 3 and leave a gap there. I want to close that gap, which means I'm going to have to move all the numbers behind it up one spot. Which, once again, if I'm working with a very large array, this is going to become a time consuming process. Now, with linked lists, we know that with linked lists, if I want to insert a value or remove a value from a linked list, it doesn't take long. It's just a matter of creating a new link object, manipulating a couple pointers, and then voila, I'm done. So with linked lists, inserts and removes are not the issue. However, I can't do a binary search on a linked list because linked lists don't provide indexes like arrays do. If I'm going to search for a value in a linked list, I'm going to have to do a old-fashioned linear search, which means starting at the front, then checking the first value, then the second, so on and so forth until I find the value I'm looking for. And again, if my linked list is storing millions of values, this can be a very time-consuming process. Binary search trees, as you will see later down the road, do not have any of these issues. Alright, well, before we get into how binary search trees work, let's just introduce some more vocabulary. Here's my entire tree. The node at the very top of the tree, we call that the root of the tree. Alright? Now, if you look to the left of the root, you'll see a mini tree. You say 28 is the root of that mini tree. And if we look to the left of 28, we can find another mini tree, of which 18 is the root of. These mini trees we call subtrees. A subtree is any tree consisting of a node, that node's children, its children's children, and so forth. The root of a subtree does not have to be the root of the entire tree. Another important word is the word path. Now, what do I mean by path? By that, I mean, suppose I ask you, how do we get from node 50 to node 55 down at the bottom? And the only way we can get there is to use the edges that connect the nodes. Well, there's only one way to get from 50 to 55. To do that, we'll have to go to 74, then to 62, before finally reaching 55. Thus, the path consists of nodes 50, 74, 62, and 55. A path is the sequence of nodes that must be visited in order to go from point A to point B on a binary search tree. In front of you is a node with 0 children. A node that has 0 children is called a leaf node. And no, a leaf does not have to be by itself in the tree. Even in a big tree with many nodes, the nodes that you see at the very bottom that have no children, those nodes are called leaf nodes. Another word you may hear me use often is the word visit. Usually when I say I'm visiting a node, that means I'm doing something important at that node. It could mean I'm printing the value at that node, or maybe I'm modifying the value at that node, or maybe I'm deleting that node. Perhaps I'm removing it from the tree altogether, or I'm inserting a new node in its place. Anytime you hear me say that I'm visiting a node, that means I'm doing something significant at that node. Another important word is the word traverse. To traverse a binary search tree means to visit each node in that tree in a specific order. There are several different ways to traverse a tree, and each way is very useful depending on what exactly you're trying to do with the tree at that point in time.